Hi, everyone. Let's talk about something called colligative properties. Yeah, that sounds a little scary. At least that's how I felt about when I was a student. I remember thinking, colligative properties? What the heck is that? Never even heard of that word. Okay, well, colligative properties are simply properties, go figure, properties that depend only on the number of particles or molecules or ions that you have and not the identity. So it's actually kind of cool. It's very general. It just means, hey, as long as you can count all the things that are present, you can make some really valid predictions. And it's not so important that you know it's like potassium or chromium or silicon or whatever molecule or whatever particles it might be. It's kind of cool. It's very general. It's similar to using the ideal gas law, right? PV equals nRT. They start the pen. So off here in the margin, PV equals nRT. So if you know the pressure of a gas and its volume, and let's say you count up the number of molecules, you can predict the temperature. As long as you have R, you can look that up. Or let's say you don't know the volume, and you got the pressure, the number of moles, and the temperature, and you can look up R, you can calculate the missing variable. And it doesn't matter which gas it is. It works for helium gas, oxygen gas, carbon dioxide, steam, methane, some crazy funky hydrocarbon. I don't know. It doesn't matter. It doesn't matter what the identity is. It just depends on the quantity. So in this case, the number of moles for the ideal gas law. So in a sense, this is it's not really a colligative property, but it's very similar in the fact that you don't need to know which gas you're talking about. This equation works just fine for all of them. Okay, so we're going to see some properties here that depend only on how many of things you have, the particles. It doesn't matter what the identity of those things are. I think there's 4 main ideas. So let's knock them down one at a time. Okay, first idea. Solutes lower the vapor pressure of the solvent. Okay, so let's go over a couple definitions. Solutes are the things being dissolved in the solvent, and together they make up a solution. So we had a list of definitions in a previous video, and in that video we said, hey, a solution is a mixture of 2 things. They can be any 2 things, even like brass, a mixture of copper and zinc, I believe. So 2 metals makes a solution. Brass, wait, brass is a metal, a hard piece of solid. The chemist doesn't care what the physical state is, whether it's a gas, liquid, or a solid. A solution is simply a mixture of 2 or more things. Now, most frequently in chemistry, solutions have one component as water, so an aqueous solution. And then the other thing is, well, are you putting in hydrochloric acid? That's the solute. Are you putting in some sugar? That's the solute. How about some sodium nitrate? That's the solute. Whatever you're dissolving in the water is the solute. And then the solvent, most of the time, will be water. And certainly for this video, we're just going to be dealing with water as a solvent, aqueous solutions. Okay, so here's the idea. It's actually true for any solvent, gasoline, kerosene, ethanol, whatever, diethyl ether, I don't know, whatever solvent you're working with. If you put it in a container, we'll put water in this container, and then pour it in as a liquid, seal it up, and then you'll see this pressure hit some value. And what's happening is, assume it's under vacuum first, sorry, and then it'll go from 0. I don't know where 0 is on this gauge, but anyways, it would increase up to some value. There would be pressure, a gas pressure in there. What's happening? Well, the liquid water, even at room temperature, will just evaporate a small amount. And right, so some of the water molecules have some kinetic energy that they collide with each other, and every once in a while, one of them collides and knocks one of the water molecules on the surface up into the gas phase, and it bounces around as a single water molecule. And unbound water molecules bounce around in the atmosphere are water molecules in the gas phase. Or you could say it's in the vapor state. And so it's not really steam. When I think of water being hot steam. It's more like humidity. So it's a humid air here, some water vapor in the air. And where'd that water vapor come from? It came from the evaporation of the liquid. That water vapor is a gas. Gas has pressure. And so we call the pressure of this gas, or the pressure of the vapor, yeah, the vapor pressure. Okay, and it has some vapor pressure at some temperature. If you heat this up, more water evaporate and increase the vapor pressure because there will be more gas molecules. If you cool this down, some of the gas molecules will collide with the surface and stick to the liquid and condense, go from gas to a liquid, and there'll be fewer gas molecules, water molecules, humidity in the gas region of this container, and the pressure will be lower. That's what solvents do. They naturally just evaporate, creating a vapor pressure of that gas vapor that they're evaporating. Okay, here's a phenomenon that's a colligative property. Put in some sugar, or put in some salt, or put in, I don't know, anything that dissolves in the water, and watch the pressure gauge now. Even though the two things are at the same temperature, the vapor pressure will be lower in the container where the liquid is a mixture, where it's not pure water or whatever solvent you're dealing with. Now, why is that? Well, there's kind of two ways of thinking about it. The solute, the molecules that are being dissolved in the water, they're actually everywhere uniformly, homogeneous solution. And sometimes the solutes are at the surface. And so they're kind of blocking the exit, right? So as the water molecules are bouncing around in the liquid form, collide with each other, well, maybe one of them is trying to collide with the bottom of a water molecule and knock it out as a gas, help it evaporate. And then sometimes it collides with a solute at the surface. And you might think, well, then does a solute evaporate? Well, the trick here is we're going to choose a non-volatile solute. What non-volatile means is that it doesn't evaporate. Volatile means it does evaporate. So gasoline, if you're at the gas pump and you spill a little bit, very quickly the gasoline, the liquid gasoline, will vaporize, evaporate, and the concrete will dry up as the gasoline evaporates from it. It's a volatile solvent, gasoline. Water is a volatile solvent because eventually a puddle of water will evaporate. It doesn't have to boil first. So throw in something like sugar, salt, or something that normally doesn't evaporate by itself at room temperature. It's not evaporating, it's non-volatile. Okay, so then if a water molecule collides with the bottom of a solute, sorry, it doesn't evaporate. It might bump a little bit, but it'll stay stuck to the liquid and not evaporate. Okay, so that, just these collisions will cause these collisions with the solute at the surface will cause fewer water molecules to escape, fewer water molecules to evaporate. Less gas means less pressure. The other idea is that the solutes are sticking to the water molecules through intermolecular forces. That's why it can dissolve. Like dissolves like. The solutes, if they can dissolve, then they have similar intermolecular forces and they can stick to the water molecules. And so the presence of these solutes kind of holds the water molecules together at the surface, and it's a barrier to them escaping as a gas. It blocks or kind of disrupts the evaporation of those water molecules. Okay, that's the idea. And more solutes will mean a lower vapor pressure, right? If you have no solutes, you're at the maximum vapor pressure. You start adding a little bit of solute, fewer gas molecules, lower vapor pressure. Adding more solutes, even lower, and so forth. Cool. That's the main idea. I'll explain why. Sorry. Fewer solvent molecules at the surface, so fewer solvents can evaporate. Second point, solutes now raise the boiling point of the solvent. Wait, why? Well, let's go back to a previous definition in a previous video where we defined boiling point a little bit more precisely. A long time ago, we did give boiling point a crude definition. We just said, hey, that's the temperature which a liquid changes into a gas. And it turns out that's not a very accurate definition. You spill some water, liquid water, on the sidewalk, on a cool day or a hot day, or I spill it in my house and I'm lazy and I don't want to mop it up, it can come back later and there'll be less water. And the water didn't boil, but it did change from a liquid to a gas. It evaporated. So boiling point, yeah, you can think of it, that's where a liquid changes to a gas, but more precisely, the boiling point is the temperature at which the liquid's evaporating so fast, it's so hot, it's evaporating so quickly that the gas it produces has enough pressure that equals the external pressure. Or in this case, it equals the atmospheric pressure. And so at the boiling point, whoops, not there. Let's put over here. Let's have a beaker of water that's under a flame. That's supposed to be a flame, nice and hot. And then the water in here is starting to bubble. What gas is inside these bubbles? Steam, right? So as you heat it up to the boiling point, and the boiling point is 100 degrees Celsius for water, it starts bubbling. Well, why? Well, it's evaporating so quickly that it can begin to evaporate within the liquid. And usually at the bottom of the beaker or the pan, whatever, that's the hottest. That these water molecules require so much heat energy that they bounce around and push all their neighbors away, and they unstick from their neighbors, and you got single water molecules bounce around in the gas phase inside a little bubble, a gas bubble, a steam bubble that will then float up because it's less dense floats, and then come up here and pop and release more steam. Okay, and so that's a better definition of boiling point. It's the temperature at which it evaporates so quickly, the vapor pressure equals the external pressure. Okay, but why does solutes then raise that boiling point? Well, it has to equal the external pressure, the vapor pressure does, right? And we just said, hey, if you add more solutes, less gas comes off. So at 100 degrees, that's when water's supposed to boil. That's when you're supposed to see little gas bubbles, steam bubbles start to form. But you don't if there's something dissolved in the water at 100 degrees. Well, the solutes are preventing the water molecules from evaporating. So you don't have enough gas to create a vapor pressure equal to the external pressure. So you need to heat up past 100 degrees to get more water to evaporate until it can match the atmospheric pressure. The vapor pressure will increase as you increase the heat, you increase the temperature. And you have to do it beyond 100 degrees to get the evaporation that occur fast enough that now you can get bubbling, you can get boiling. So more solutes means higher boiling point. Yep, a higher temperature is required to cause more solvent to evaporate and to increase the vapor pressure. So that can equal the external pressure. That's what will allow it to boil. So I found this cool little meme somewhere on the internet. Friends, keep you cool. Yeah, so these are the non-solutes, a lot of them, so it's concentrated, a lot of solutes in here, and that will slow down the evaporation of water, causing it not to boil 100 degrees, but makes it harder to reach the boiling point. You have to go above the boiling point of pure water so that the solution, the mixture of solute and water, can boil. And then we can throw some math in here. So it turns out there is some theory to help us predict what will be the new boiling point of the solution if we know how many solute particles are dissolved. And we also have to know the quantity of water. Okay, so here's the equation. You don't have to memorize it. I'll give it to you on the exam. You just need to be able to use it. Okay, so the equation is the change in temperature, the change in the boiling point temperature, is equal to 0.51 times the moles of solute divided by the kilograms of water. The 0.51 is a conversion factor. This is only valid for water. If you dissolve, I don't know, little pieces of grease or candle wax or something into gasoline, and gasoline's your solvent, well, then you're going to get a new conversion factor specific for gasoline. The little pieces of grease or the candle wax, whatever you're putting into gasoline, that will be a solute in gasoline, and the boiling point of gasoline will then increase with more solute particles. It doesn't matter what you put in there as long as it dissolves. But we're going to stick to water, so our equation has 0.51. That's specific to water. Solute, you then have to count up the number of moles of particles. We have an example down here to clarify. And then you have to divide it. The little slash means divide by the kilograms of water. One common mistake on exams is that students are really good about finding this equation, putting in the right numbers, and cranking out an answer, and then they think they're done. The question oftentimes asks, what is the boiling point? And this equation doesn't tell you that. It tells how much it's changed. So the actual boiling point is the amount of change that you just calculated plus 100 degrees, the boiling point of pure water plus the amount it changed. And that'll give you, add the two together. That gives you the true boiling point. All right, let's give it a try. Let's scroll up a little bit, get more room, a little more room. There we go. Okay, sample problem. What is the boiling point of a solution of 3.6 moles of, remember your polyatomics? Polyatomic ions, NH4 plus is the ammonium ion. And PO4 3 minus is phosphate. I guess you don't have to name this in order to do this problem, but hey, it doesn't hurt to refresh our memory about the names of the polyatomic ions. So what is the boiling point of a solution of 3.6 moles of ammonium phosphate dissolved in 250 grams of water? Okay, so first calculate the change. Change in temperature is equal to 0.51, I'm just copying it down, times the moles of solute. Okay, there are 3.6 moles of this whole molecule. So we put in 3.6 moles of this molecule. Wait, but then this thing dissolves in water. Does this remain, all these atoms, do they remain stuck together when they dissolve in water? Or what do the solubility rules tell you about ammonium phosphate? Well, rule number one of the solubility rules is that if it contains the ammonium ion or the alkali metals, it should be soluble. Is this ionic or covalent? Because covalent molecules can dissolve, but they stay tightly bound together if they're covalently attached. No, ammonium is a cation, and phosphate is an anion. If an ionic compound dissolves, it splits apart into new particles, into cation and anions. So we have to properly count all the particles of solute. So we have to know that this molecule falls apart when it dissolves. So if you have the solid, so I think that's what someone did. They weighed out and then calculated 3.6 moles of this solid, dumped it in the water till it dissolved, and then started heating it. Well, dumped it in 250 grams of water, started heating it, and it's taking forever to boil. And they're wondering, well, what is the boiling point? Hey, let's calculate it. And you have to know that this is an ionic compound. When ionic compounds dissolve, the cations separate from the anions. So you kind of do have to know your polyatomic ions. You have to know that the N and the H don't separate from each other. Well, they're nonmetals. Nonmetals are held together by covalent bonds. So the N's and the H's will stay stuck together covalently. But the whole ammonium ion separates from the whole phosphate ion, and there's 3 of them. And after the phosphate unsticks, all these ammonium ions are all positively charged. They all repel each other with the same charge. So you can get 3 ammonium cations and 1 phosphate ion. And those would be aqueous. And if we're counting particles then, how many things do we get out? You start with 1 thing. Actually, you're supposed to start with 3.6 moles of it. But let's just look at the main idea. If you take 1 of them, it produces 4 more ions. Not more ions. It actually produces 4 ions. So the true number of particles is 3.6 times 4. That's how many moles of solute that we have. How many particles? I know it doesn't matter what we have, it just matters how many. And so if it's ionic, you have to count up all the cations and add them to the number of anions, and then multiply it by the number of moles of the original salt, the original compound. And then divide, this little slash means divide. I'll draw it this way. by the number of kilograms of water. Oh man, they didn't give us kilograms. We got to convert it. So use dimensional analysis, unit conversion, and say, hey, what do you want? I want kilograms of water. Put a little equal sign, put a line there. And what do you have? Or what do you know? I know I have 250 grams of water. Okay, I see what I want. I am given this. How do I have to find a conversion factor that will cancel out my grams and change them into kilograms. Don't bother looking at the top of the exam or the sample test. It's not there. This is one of the conversion factors I want you to know. You need to know that 1 kilogram is equal to 1,000 grams. Yeah, just like 1 kilometer is equal to 1,000 meters. Okay, the kilo means 1,000 of whatever else you have. Okay. All right, so then do the math. The grams are canceling out. It's going to give us kilograms. So 250 divided by 1,000. If you get your calculator out, you'll find it's 0.250 kilograms. And that goes on the bottom. How many kilograms of water? 0.250. On the exam, I think, no, maybe I don't. I can't remember. Anyways, as long as you use 0.51 and you have units of moles, we do, and units of kilograms, we do, automatically the number will be in degrees C. So you get your calculator out or your piece of paper where you did the calculations earlier, and you'll find, there it is, 29. The answer, the change in temperature is 29 degrees C. Is that the new boiling point? No. Water boils at 100. And if you had solutes, the temperature's boiling point is supposed to go up, and 29 is not above 100. No, you have to add it to 100 degrees, right? So the new boiling point, or actually the boiling point of this solution, the mixture, is 100 plus 29. It's 129 degrees. There you go. Wow, that's actually pretty high. Be careful with that. Man, steam can burn. This stuff is going to really leave a mark. So be careful with that solution. All right, that's the second colligative property. First one was vapor pressure lowers as you add more solute. Second one is as you add more solute, the boiling point increases. Next one is if you add more solute, the freezing point lowers. Everything's opposite chemistry, right? So we'll make a quick note here. More solute increases the boiling point, but it decreases the freezing point or the melting point. Now, why is that? Well, if you remember, there's a video I made about changes of state, where we talked about solids, liquids, and gases. And in that video, I had a picture of water. I should have found it. Sorry, I didn't. Water, when it freezes, gets into a nice, neat, ordered array. It kind of looks like a honeycomb. These hexagonal arrangement of water molecules, three-dimensionally. And it's a nice, uniform pattern. And that's what ice looks like on the molecular level. When you look at liquid water, the water molecules are willy-nilly, all oriented randomly, still touching, sticking together as a liquid. And in a solid, they all have to get in a particular shape, orientation, and they all arrange themselves very neatly into like a honeycomb network. Well, if you put in some solutes, as the water is attempting to freeze and get into these right positions, the solutes get in the way. And so you need to cool the solution even farther to encourage the water molecules to find their spots, get into their crystal structure, and freeze out as a solid. So adding more solutes disrupts the crystallization process, will disrupt solvent molecules from sticking to other solvents. That's what needs to happen in order to form a crystal, in order to form a solid. Okay. So adding solutes or solutes increases the boiling point, decreases the freezing point. And so we take advantage of that In the wintertime, if you live in the Sierra Nevadas or out in Minnesota somewhere, you know, during the daytime, some of the snow will melt and create a puddle on the sidewalk or on your driveway. And the next morning, overnight, it'll freeze up. And that's a slipping hazard. You can fall and get hurt. So you can go out there and chip it off the sidewalk. There are some ice picks they sell in Minnesota. Or you can be lazy and just sprinkle some salt on it. And it turns out that adding salt to the ice will lower the freezing point of the ice. The salt will actually start dissolving in the ice, and it'll actually lower the freezing point. So as long as it's not too cold outside, the salt will melt the ice. It'll cause it to freeze. Water will then be required to freeze at a much lower temperature than 0 degrees Celsius. So you can throw ice on the sidewalk to melt the ice. You can also add salt to ice to make a very cold solution, something that's even colder than 0 degrees, and you can make homemade ice cream, right? So if in here in this container you have some cream, some vanilla, some sugar, any other ingredients for your ice cream, if you use just normal ice at 0 degrees is not cold enough to freeze cream and make ice cream. No, you have to get the ice even colder. And one way to do it is add a lot of salt, rock salt, crude salt. It's actually fairly cheap. So you need a bunch of it to get the ice and the salt to form a mixture that's cold enough so it can start to freeze the cream. And then the trick is to keep stirring this to get a nice creamy frozen mixture. Now I want some ice cream. Anyways, nice way of using a colligative property to get by in life. Okay. For us in chemistry, though, that would be a fun lab if we made some ice cream. That'd be cool. You're not supposed to eat in the lab, though. Anywho, on the exam, I might ask you to predict what will be the new freezing point, which is the same as the melting point, if you have a solution and not pure water. And the equation looks very similar. Again, I'll give you this equation. You don't have to memorize it. The change in the freezing point is equal to this conversion factor, a negative 1.86 times the moles of solute. So again, count up the particles and divide it again by the kilograms of water. It's still water, but we're not boiling it, we're freezing it. So that's why the number changed from 0.51 to 1.86. And then this minus sign, why is that there? Oh yeah, the temperature is supposed to go down, it's supposed to decrease. So that's why there's a minus sign. It's going to be a lower temperature. But then you got to remember, wait, that's the change in temperature. You need to add it to the actual temperature. Oh, okay. So this is a much more forgiving equation. The actual temperature of water is 0 degrees Celsius. So if you happen to forget to add 0 to this, you still got the right answer. So if you're freezing it, we luck out. If you calculate the change in temperature, that is actually the freezing point of water because you add the change in temperature to 0 and you're left with the change, which now that's the actual freezing point. Cool. Let's illustrate in another sample problem. Okay, let's take, get a little more room here. Let's take 2.5 moles of calcium chloride and it was added to 750 grams of water. What's the freezing point of this solution? Well, go grab the equation right there. Change in temperature is equal to negative 1.86 times moles of solute. Well, there's 2.5 moles of these salt molecules, calcium chloride. Well, that's the solid chemical formula, but when you dissolve it into water, is this ionic? I should have brought the periodic table. Calcium's on the left side of metal. Chloride is on the right side of non-metal. And that means, yes, this is ionic, a metal with a non-metal. And when it dissolves in water, solubility rules help me out. The second solubility rule is that the halides, chloride, bromide, and iodide, are usually soluble, except with silver, lead, and mercury. Ooh, and calcium is not silver, lead, or mercury. So yes, solubility rules predict this should dissolve. And when it dissolves, it separates into ions because it's an ionic compound, right? Metals with nonmetals. And then what are your charges? Well, calcium, go look up. It's in the second column, an alkaline earth metal. At the top of that column, there's a 2, meaning there's 2 valence electrons. And the metal, calcium, likes to lose both of them to form a +2 cation. The chloride ions, they're in the 7th, or next to the last column. The valence number above the column is 7. It wants to acquire one more electron to have 8, an octet, and each chloride wants to do that. So the charge on the chlorine is a -1 when it's ionic. And you don't say, hey, this turns into Ca plus Cl2. No, no, no. The chlorides are all both negative. They repel each other. And you get 2 individual anions for a total of 3 ions. So the true number of solute particles is 2.5 moles times 3. And you divide it by the kilograms of water. Darn it, it's grams of water. So do a quick conversion again. We have 750 grams. We divide it by 1,000 grams to convert it to kilograms, which means sliding the decimal place over 3 positions. 0.750 kilograms. And now we have the right equation. Put that in our calculator. And I got, yes, I got negative 18.6 degrees C. The actual boiling point, sorry, actual freezing point is 0 plus this. Oh, well, this is also the freezing point of the solution. That's pretty cold. You know, they actually sell calcium chloride that you can sprinkle on the sidewalk. You can also go to the grocery aisle or somewhere else and buy some sodium chloride. Which do you think is more effective at melting ice? Well, sodium chloride only has 2 ions. Calcium chloride has 3. So mole for mole, calcium chloride is more effective. Now you have to check the price and see if you're getting a good deal. Anyways, because you could just throw more moles of sodium chloride on the sidewalk. That'll also lower the freezing point. Anyways, interesting comment. What else we got? That's the 3rd colligative property. Last one is osmosis. There we go. So maybe you've heard of osmosis. If not, here's a definition. Osmosis is the movement of a solvent, and this most of the time it's going to be water. A movement of water through a semi-permeable membrane from high water concentration to low water concentration. Okay, let's break a few things down here. Semi-permeable. Okay, semi means partially, half and half maybe. Yeah. Permeable means to penetrate. So not everything penetrates. So ideally, we have a membrane. It could be a cell membrane. It could be a cell wall. It could be some type of plastic that only allows some molecules to penetrate. Some type of artificial or natural membrane. And semi-permeable means some things can go through and others cannot. And in this case, we're only going to allow water to go through. Other molecules, other solutes cannot. Okay, so here's the situation in the lab. You might get a piece of glass tubing that's bent into a U shape, and then plug up the middle of it with this semi-permeable membrane. And then fill one side with pure water, and the other side, make it an aqueous solution with your choice of solute. Could be sugar, could be table salt, could be calcium chloride, ammonium phosphate, anything. It doesn't matter, right? The identity doesn't matter. What matters is how many of those you put in, how many solutes are in there. The other thing we need to know is that nature just naturally diffuses, substances rather, naturally diffuse. They spread out. It has to do with entropy. Things are going from ordered, like everything over in this neatly placed corner of the room, and then later, hey, it's all over the place. What happened here? Entropy. Or the little kids got in here and kicked things around. Dog came in here, cat, whatever. Wind. Things just naturally spread out. So if you have a big bathtub and you put some bath salts at one end and you don't stir the bathtub, eventually the bath salts will spread out throughout the bathtub. And it isn't just the bath salts. It can be food coloring, it can be anything. Or in this situation, it can be water that's spreading out. So the barrier here prevents any of the sugar, sodium chloride, whatever you got in here, the solutes from going through. They have to stay on the right. The water, however, is free to go either way. And now nature says, the left side is pure water. It's highly concentrated water. We have tons of it. The other side has less water. Let's make these things equal. So the water starts flowing through here to dilute this down, make it more water, make the water concentration higher. And the idea is that as water leaves, it was supposed to reduce the water concentration over here, but it doesn't. It's still the same number of water molecules per liter. So it turns out if you're in outer space and there's no gravity, eventually all this water will go to the other side as it attempts to spread out and make both sides equally concentrated water. But we're here on planet Earth where there is gravity. So what happens is the water, nature says, okay, spread out, try and balance it out. Both sides have the same concentration of water. Well, I can't do that. Water keeps flowing and flowing and flowing, and more water piles up on this side, and this height gets higher and higher. And now there's more water on this side, so there's a higher gravitational force on this side. Gravity starts pulling down on this column of water, and it starts squeezing the water back to the other side. And then the water pushes back, and eventually you reach this equilibrium, where through osmosis, the water's trying to balance out, spread out uniformly, and then gravity is trying to resist that, this piling up of water over here and trying to balance it, having equal heights, gravity pulling down on this. At some point, gravity's pushed downward, and the osmotic force this way reach some balancing point, and then you can actually calculate the osmotic pressure that's keeping this column of water elevated. Isn't that crazy? On the other hand, knowing that gravity is pushing us down and preventing from all the water come over, gave people an idea. They realized, hey, what if we help gravity out and we force this down? Let's put a little plunger, a little rubber seal so the water can't leak out, and just start pushing on this. Push so hard, it actually pushes the water through to the other side. Well, as long as you don't rupture the membrane or tear it, all the solutes have to stay over here, and only the water can pass through. And you're going in the opposite direction of osmosis. You're reversing osmosis, and you're actually generating pure water. So here's some water that has been purified by reverse osmosis. I don't know if you can read that, it's pretty small print. But next time you pick up a bottle of water or purified water, see how it's been purified. It might have been done through this technique, reverse osmosis. Cool. All right, here comes some math. Go back up to this top slide. If you put in more particles, the water will have a greater tendency to dilute this down, and the osmotic pressure will increase. If you have fewer solutes, so imagine a situation both sides have pure water, then there's no flow left to right. The concentration of water is going to be the same if both sides contain pure water. And then just sprinkle a few particles of something that dissolves on the right side. Well, now there's a few solutes in here, but the water concentration has gone down. There's fewer water molecules per liter. So now the water will start to move over a little bit because you only have a few solid molecules. More solutes, more pressure, more flowing of the water. Well, we can measure that, how much it flows over, if we have an idea how many particles are in here. So there's something called the osmolarity that takes that into account. You know about the regular molarity, that's the number of moles of solute divided by the liters of solution. Well, the osmolarity is where you take the number of moles of solute and multiply it by the number of ions that it creates, or the number of solute particles. Okay, and we've been doing that before when we were calculating the freezing point. It wasn't the osmolarity though. Here we go. We said that, hey, we had 2.5 moles of the calcium chloride, and each calcium chloride produces 3 ions. So let's multiply those two together. If we had divided by the total volume in liters, that would be the osmolarity. Okay, here I just want osmolarity. So do the same technique. Get the number of moles of solute, multiply it times the number of particles, usually it'll be the number of ions, and divide it by the liters of solution. And that will be the osmolarity. Here's a quick sample problem to demonstrate. What's osmolarity of 0.2 molar sodium sulfate? Okay, well, osmolarity is equal to the actual molarity, 0.2, times the total number of solutes. So what does sodium sulfate do when it dissolves? So if we start with solid sodium sulfate, dump it in the water, well, sulfate, you might remember from one of the polyatomic ions we had to memorize. But we're putting these polyatomics to work, aren't we? Yeah, it's actually, sulfate has a -2 charge. But you know what? If you could recognize that the chemical formula has been given, you could probably figure that out. Go to the periodic table and look up the charge of sodium. It's in column 1, alkali metal, and it has a +1 charge. And there's 2 of those. So to make a neutral compound, if you have 2 pluses, the sulfate must be a -2. And altogether, 2 cations, 1 anion gives you 3 ions. So you have to multiply this by 3. And then the number is 0.6, right? 3 times 0.2 is 0.6. And then your units will be osmoles per liter. I know, it's a little weird, but molarity is moles per liter. The os for osmosis is to take into account the colligative property that depends on how many particles are in there. Not just how many moles of your original compound, but let the compound dissolve, break down the ions, and then get the actual count of solute particles. So osmolarity is a way of counting that and telling the reader that's what we've done. We've already counted it. Here's an application of osmosis, a very important one. Hey, in a previous video, we talked about heparin on the right side. It's a blood thinner. So maybe people who suffered a stroke might have to keep their blood thin so it doesn't cause another clot, cause another stroke. There's other reasons why someone might have to inject themselves or get injected with heparin. I'm not a doctor, so I should go look up things. Anyways, stuff exists, and it's an important medication, and it has to be injected. But to minimize the damage from the injection, you have to dissolve heparin, it turns out, in a 0.9% sodium chloride solution. Sodium chloride, that's not a medicine, that's just table salt. What's that doing here? It's increasing the number of particles in the solution. It's trying to keep osmosis from doing some damage. So here's the idea. If you go into the bloodstream, that's a red blood cell, you got the blood here, and it turns out blood is an aqueous solution. Go figure. Yeah, it is. Sorry, just being silly. Inside the red blood cell is the cytoplasm, which again is an aqueous solution. So inside the cell, there's DNA, there's RNA, there are proteins, there's ATP, there's some ions in there. There's a whole bunch of things dissolved in the aqueous solution inside the cell. Outside, it's the bloodstream, and there's blood proteins, there's salts in there, there's blood sugar, glucose, there's other things dissolved in the blood. And it turns out the number of particles in the blood is the same as the number of particles inside the cell. There's not supposed to be any DNA in the blood, but it doesn't matter what it is. It doesn't depend on the identity. It's only dependent on the number. So the blood has a lot of things dissolved in that aqueous solution. The cytoplasm has a whole bunch of other things dissolved, but it turns out they have the same numbers of molecules dissolved. And so water is free to flow through this semi-permeable membrane, the cell membrane, freely. So water can go in, water can come out, and they're balanced. We say that is an isotonic solution. The blood is isotonic to the cell. Water freely goes back and forth. It's nice and balanced. Down here we have a plant cell, and this thick outer coating is a cell wall, and the little thin line here is a cell membrane, and the same idea. In a normal plant, each plant cell is in an aqueous environment, wherever you find this cell in the living part of the plant, stem, leaf, root, wherever water is around, and it's supposed to have the same number of particles in the, I don't know what it's called in a plant. It's not blood. And the liquid environment around the plant cells has the same number, doesn't have to be the same identity as the particles dissolved inside the plant cell. Water is free to flow in and out through this semi-permeable membrane. Actually, membranes plural. There's a membrane plus a cell wall, and the cell wall allows water to permeate it, but not much else. Think carbon dioxide can go back and forth between the two. Oxygen, certainly. How else is oxygen going to bind to the hemoglobin inside the red blood cell? So gases can go back and forth as water can too. Okay, if you were to inject heparin into the bloodstream with pure water, well, heparin is a solute, but you don't have enough in there. So at the injection site, you have a lot of water and only a few solute particles, heparin, if you leave out the salt. And what happens is the environment of the red blood cell has too much water over here. No, too much water over here. Sorry, I should have taken a break. Do that again. Start with, so inject with just heparin, and water. So in the environment, you inject this in the bloodstream, there's too much water. We didn't have enough solutes in here at the injection site. And so now we don't have things balanced. It's no longer isotonic. There's too much water at the site of injection. So more water can flow through the cell membrane and make it swell, potentially bursting it. Not only red blood cells, but tissue nearby. At this point of injection, if you inject in the muscle, well, now there's too much water. The water can flow into the nearby muscle cells and make them expand, possibly rupturing them. Okay, that's going to be painful. Same thing happens to a plant, but it's protected by the cell wall, preventing it from rupturing, but you can see that it does swell up. In this case, there's too little solutes in the solution, in the environment. We just injected mainly pure water with a little bit of solutes, a little bit of the heparin. There's too little solute. So relative to the cell, if the cell looks outside and says, whoa, there's too little stuff dissolved, it's hypotonic, not isotonic. How are we going to remember these words? Isotonic reminds me of isomers. So did we talk about that? Isomers are different molecules, but they have the same chemical formula. And there it is, the word same. There's isotoner gloves. Did they fit perfectly because of the same size as your hand? I know, I'm reaching. But iso means the same. There's an S in there in iso. So there's S in same. Same number of solutes. Same osmotic pressure. They match. So water flows in. As water flows out, it's equal. No disruption of the cell volume or shape. But if it's hypotonic, I think about a hypodermic needle that goes under the skin. If you're diabetic and your blood sugar goes too, is it diabetic? No, that's the other one. There's another condition where you do have too little blood sugar and then you're hypoglycemic. Hypo again means too little, below. Hypochlorite has too little oxygens, that's ClO minus, and then perchloric has too many, 4. Anyways, hypo means too few. So if the environment has too few solutes, hypotonic, that can cause cells to expand, possibly rupture. The reverse case is just as bad. It can cause damage too. Too many solutes means there's too little water. So inside the cell, there's actually more water. The concentration of water is higher than outside. So more water comes out of the cell, and now the cell shrivels up. Here we got a plant cell that's shriveling up, but the cell wall is still trying to maintain its shape. Yeah, because we have too many solutes. And nature says, hey, water spread out. It's too much water inside, so flow outside to try and balance the water concentration. And it ends up drying up the cells, even though it's in an aqueous environment. That's because the solution is hypertonic. Okay, so I think about giving a whole bunch of sugar, too much sugar, to a bunch of kids, and they just go hyper, bouncing off the walls because they have too much sugar. Okay, so that's what's happening here. There's too many solutes. Could be sugar, but it could be anything. We don't care about the identity. Just too many things dissolved, and the water will come out and cause these to shrivel up. In biology, I don't know if they still do it, but you can preserve specimens in brine. So brine is a concentrated solution of salt water. You put some leaves in there or something else you want to preserve, and it'll actually drain the water out of the specimen, the cells. The water will go into the salt water, the brine solution, and dry them out. And effectively, well, it kind of kills them. But if it's a plant, it'll maintain its shape, and then you preserve the structure. Let's see, what else do we need to know? I think that's about it. Oh, 0.9. That turns out to be the number of solutes that matches the number of solutes inside the red blood cells. It matches the number of solutes in the blood, in the tissues. That's why the heparin is injected with a solution of 0.9% sodium chloride. Maintain an isotonic environment. Minimize the damage at the injection site and damage by osmosis. Okay, and so there might be something like this. As a sample problem, wow, that's it. Is a solution of 0.2 molar sodium sulfate isotonic, hypotonic, or hypertonic to a cell at 0.3 osmoles per liter? I did a quick calculation. 0.9% sodium chloride is about 0.3 osmoles per liter. The 0.9% is probably a weight volume percentage. We talked about that measure of concentration. So I changed it to osmoles per liter with 2 ions, sodium chloride. Anyways, that's the question. Hey, what if this solution's exposed to these cells, plant or red blood or whatever cell? Would this environment be isotonic, hypotonic, or hypertonic to that cell if the cell is at 0.3? Well, if you're lazy, you might say, oh, 0.2 is smaller, so therefore 0.2 is hypotonic. Ooh, but you have to calculate the osmolarity. The osmolarity of the solution is the molarity, 0.2 molar, times the number of ions. And there's 2 sodiums and 1 sulfate, 3 ions. And it's actually 0.6 osmoles per liter. That's the actual osmolarity. Now compare. 0.6 is higher than 0.3. So this sodium sulfate solution is actually hypertonic. There we go. That's how you do it. And I think we're done. Let me double check. Anything else over here? Nope. Okay, so just to review real quickly, there's 4 colligative properties, properties that don't change as you change the identity, as long as you count the numbers. The vapor pressure decreases as you increase the number of solutes. The boiling point goes up. Where's that? We have that picture over here. Boiling point goes up. There it is, as you add more solutes. The freezing point goes down as you add more solutes. And the osmotic pressure goes up as you add more solutes. Cool. That's enough for now. I'll see you in the next video.